Hi, good morning. I am Srinivasulu Vempati, Assistant Professor of Chemistry, Nagarjuna Government College, Nalgonda. In the last two classes, we have discussed something about nitrohydrocarbons. Today, we will finish remaining part of this chapter. Before going to the class, I will recap once again what we have learned in the previous lectures. What are nitrohydrocarbons? Nitrohydrocarbons are the compounds, organic compounds containing NO2 as a functional group. The general formula of these compounds is RNO2. For example, nitromethane, nitroethane, nitrobenzene, nitronaphthalene, etc. Classification. Based upon nature of R group, we broadly divide into two types: aliphatic nitrohydrocarbons, aromatic nitrohydrocarbons. In aliphatic nitrohydrocarbons, R is aliphatic in nature. Nitromethane, nitroethane are the examples. Coming to the aromatic nitrohydrocarbons, the R group is aromatic ring. That means nitro group is linked to aromatic ring. For example, nitrobenzene, 1 nitronaphthalene, 2 nitronaphthalene are different examples for aromatic nitrohydrocarbons. Coming to aliphatic nitrohydrocarbons, further divided into three types: primary, secondary and tertiary nitrohydrocarbons based upon nitro group linked to which type of carbon, maybe primary or secondary or tertiary. So these are the different examples for primary and secondary, and this is a tertiary nitro. This is tertiary. Why? Because in this compound, in this carbon, nitro group is linked to tertiary carbon. That's why it is tertiary nitrohydrocarbon. Okay. Then nitro group is in resonance forms. It is in between two resonating structures. Pi electron delocalization leading to formation of two forms. This is the resonance structure of a resonance hybrid of nitro group. In this structure, nitrogen is bearing plus charge. Minus charge is rotating, distributed among two oxygens and nitrogens. So this is the resonance hybrid of nitro group. Then nitro compounds, especially those which have alpha nitrogen, exhibits keto-enol tautomerism. Primary and secondary nitrohydrocarbons, because of having alpha hydrogen, they exhibit keto-enol tautomerism. Keto form is converting into enol form. So in this keto form we call as nitro form, whereas enol form we call as acid form. So these primary and secondary nitrohydrocarbons exhibit this keto-enol tautomerism, whereas tertiary nitrohydrocarbons, because of lacking alpha hydrogen, they doesn't exhibit keto-enol tautomerism. These are the enol structures of primary and secondary nitrohydrocarbons. Next, preparation of nitrohydrocarbons. We learned to prepare nitrohydrocarbons from three methods. One is vapor phase nitration of alkanes. Second is from alkyl halides. Third is from primary amines. So we learned three preparatory methods for nitrohydrocarbons. Next, chemical reactivity. So generally, nitrohydrocarbons exhibits substitution reactions generally. So in halogenation reaction, these primary and secondary nitrohydrocarbons, when they react with the halogen like chlorine or bromine in presence of a strong base like NaOH, they undergo substitution reaction in place of alpha hydrogens. So due to this, primary nitrohydrocarbon gives first in the first step monohalogen substrate. In the second step, dihalogenated. That means, for example, with bromine, nitroethane gives one nitro, one bromo, one nitroethane. For in the second step, one dibromo, one nitroethane. So that means two alpha hydrogens are gets replaced by halogens. Whereas coming to the nitromethane, when it reacts with the chlorine plus of NaOH, it is giving trichloronitromethane, which is called chloropicrin or nitrochloroform. This is halogen reaction of nitrohydrocarbons. Then reaction with nitrous acid. So this reaction we call as a white, blue, red reaction. So tertiary nitrohydrocarbons doesn't exhibit a reaction, doesn't react with nitrous acid because of having lacking of alpha hydrogens. Whereas primary and secondary nitrohydrocarbons react with HNO2. A primary nitrohydrocarbon, when they react with nitrous acid, first it gives blue compound, which on dissolving with NaOH solution, it is giving red color solution. Whereas secondary nitrohydrocarbon, when react with HNO2, it is giving only blue color solution. It doesn't dissolve in NaOH that means doesn't give a red solution. Whereas tertiary nitrohydrocarbon not at all reacts with HNO2. That means colorless. So tertiary nitrohydrocarbon gives a white color solution. Secondary nitrohydrocarbon gives blue color solution. Whereas primary nitrohydrocarbon with HNO2, it gives finally red solution. So that's why it is called white, blue, red reaction. This reaction is used to distinguish primary, secondary and tertiary nitrohydrocarbons. Then Neff reaction. Neff reaction what is Neff reaction? Salt of primary and secondary nitrohydrocarbons, when they react with sulfuric acid followed by hydrolysis, they undergo oxidation reaction giving aldehydes and ketones respectively. That means primary nitrohydrocarbons gives in this reaction aldehydes, whereas secondary nitrohydrocarbons gives ketones in this reaction. Then there is no reaction with the sulfuric acid by tertiary nitrohydrocarbons. For example, nitroethane, in this reaction it is giving acetaldehyde, whereas nitropropane, 2-nitropropane, in this reaction it is giving acetone. So this reaction is used to prepare carbonyl compounds. So by changing the alkyl group in the nitro compound, we can prepare different aldehydes and ketones. So this is Neff reaction. Reduction reactions. Nitro compounds generally undergo reduction reaction by giving its corresponding reduced products, amines, hydroxylamines, etc. So in different conditions, that means by changing reducing agent, we'll get different product. For example, nitroethane in presence of nickel undergo hydrogenation reaction, or tin HCl in presence of tin and HCl mixture, it is giving aminoethane, ethylamine. Whereas same nitroethane in presence of zinc and ammonium chloride in neutral reaction conditions, it is giving hydroxylamine, ethyl hydroxylamine. Whereas the same nitroethane in presence of tin chloride and HCl, it is giving mixture of two compounds. One is ethyl hydroxylamine and oxide, ethyl acetaldehyde oxide. So this is the reduction reaction of nitroethane. So far we discussed different reduction reactions of nitroalkanes. I am going fast. This is the recap. Coming to the aromatic nitrohydrocarbons. The aromatic nitrohydrocarbon, in aromatic nitrohydrocarbons, one of the hydrogen is replaced by nitro group. That's why we call as aromatic nitro compounds. For example, nitrobenzene. One more example is nitro and nitronaphthalene, 2-nitronaphthalene, 1-nitroanthracene, 2-nitroanthracene, or orthonitrotoluene, or are different examples for aromatic nitrohydrocarbons. In this, I told already, nitro group is linked to aromatic carbon. So nomenclature. In this nomenclature, we call as these nitroaromatic hydrocarbons. For example, first one is nitrobenzene. Second, this one is metadinitrobenzene or 1,3-dinitrobenzene. This is orthonitrotoluene or 2-nitrotoluene. This one is 1,3,5-trinitrobenzene. Okay, this is toluene. Actually, in toluene, 1, 3, 5 positions are occupied by nitro groups. That's why we call these 2,4,6 trinitrotoluene. In short, we write this as TNT, which is used as explosive. So this is in naming of aromatic hydrocarbons, we use we call them as nitroaromatic hydrocarbons. In benzene ring, to specify the name position of the nitro group, we will use ortho, para, nitro terms. Okay. Then coming to the preparation. So in this preparation, we are taking example nitrobenzene for aromatic nitrohydrocarbons. As we know, when benzene reacts with the nitration mixture at below 60 degrees centigrade, we get nitrobenzene. This is nitration method. So if the reaction temperature is increased more than 60, what happens? One more reaction takes place, further reaction taking place by giving metadinitrobenzene. This is nitrobenzene, this is nitrobenzene, and this is metadinitrobenzene. So the same reaction, same benzene with concentrated nitric acid at 100 degrees centigrade, that means higher temperature, it is giving beta-dinitrobenzene. In other reaction, when benzene reacts with the fuming nitric acid, it is giving trinitrobenzene, 1,3,5-dinitrobenzene. So all we discussed, I am giving fast recap. So when we we do the nitration with the toluene reaction, so this reaction is giving orthonitrotoluene. So we and para-nitrotoluene, mixture of nitrotoluenes, orthonitrotoluene, para-nitrotoluene. So by observing this reaction, we can say methyl group is orthoparadiactyl. That's why incoming nitrophile electrophile is going to ortho and para positions to the methyl group. Further, we observe this reaction is taking place at only 30 degrees centigrade. That means reaction is very active towards electrophilic substitution reaction because of methyl group electron releasing nature. When we compare to benzene, toluene is very reactive towards electrophilic substitution reaction because of methyl group hyperconjugation effect. So on prolonged nitration reaction, it is further undergoing nitration reaction by giving T and T, trinitrotoluene. So this is a nitration reaction of benzene. In this way, we can prepare nitrobenzene or and other derivatives of nitrobenzene. Okay, what is the mechanism? So already we learned in the mechanism when we observe the mechanism of this reaction. It is majorly two steps. In the first step, electrophile formation taking place. This electrophile, this electrophile, this electrophile. Both electrophiles forms, but this electrophile is more electrophilic in nature. That's why nitro plus NO2 plus acts as a electrophile in this reaction. This is a net reaction. What is net reaction? HNO3 and H2SO4. When they reacted, they will give these three: nitronium ion, bisulfite ion, and hydronium ion. Okay, this formed nitronium ion reacts with the benzene ring by giving nitrobenzene. So in the first step, in the second step, what happens? A sigma complex formation taking place. This on resonance stabilization, it is stabilized. So that's why stabilized sigma complex by losing 1H plus to the bisulfite ion, finally it is giving nitrobenzene. So this is a mechanism of nitration reaction of benzene. So equimolar mixture of nitric acid and sulfuric acid we call as nitration mixture, which is providing our required nitro electrophile. So this is mechanism of nitration of nitrogen. So coming to the physical properties, already we learned physical properties. Then coming to the chemical properties. So now we are starting our actual lecture here. Please listen carefully. Because of presence of nitro group in nitrobenzene, so we know nitro group is electron withdrawing nature. So because of high electronegative oxygen, this oxygen attracts electrons towards towards oxygen. So due to this, the nitro group attacks benzene electrons from benzene ring. So due to this, benzene ring gets positive charge. So we see the resonance structures of this benzene ring in ortho position, para position, and ortho position. So ortho and para positions are more electron deficient than meta position. So that's why in benzene electron density is more at meta position when we compare to ortho and para position. So this is clear. So because of NO2 group minus M effect, minus M mesomeric effect, the benzene ring is deactivated towards electrophilic substitution reactions. That's why nitrobenzene doesn't take place, doesn't undergo electrophilic substitution reactions as easy as benzene or toluene. So nitrobenzene is inert or reluctant to undergo electrophilic substitution reaction due to nitro group. Nitro group is electron withdrawing. Due to its electron withdrawing nature, benzene group becomes electron deficient. When we compare different positions, ortho para positions are more electron deficient than meta positions. Whenever the reaction takes place in rigorous conditions, an electrophile comes and attacks on meta positions when we compare to ortho and para. So this is a chemical reactivity. So once again I am telling that nitrobenzene is reluctant to electrophilic substitution reactions when we compare to benzene or methylbenzene due to minus M effect of nitro group. If the reaction takes place under rigorous condition, the incoming electrophile is directed to occupy at meta position. This is a orientation of incoming electrophile. Okay, coming to the reduction reaction of nitrobenzene. Nitrobenzene undergo reduction reaction by giving various reduced products. So if you see this reaction, nitrobenzene, when it is getting two hydrogens, it's giving nitrosobenzene. It is unstable. So why we are calling this is a reduction reaction? So NO2 group is, you see, NO2 group is converting into NO group. That means it is losing one oxygen. So losing of oxygen is known as reduction reaction. That's why it is a reduction reaction. So what happens? This nitrosobenzene is also further reduces to phenyl hydroxylamine. You see, this is hydroxylamine, NH2OH. In place of one H, phenyl group is there. That's why we call as phenyl hydroxylamine. This is phenyl hydroxylamine. This is also a reduced product. How can you say? You see, when we compare to NO and NHOH, there is two hydrogens are added to the NO group. So there is no loss in oxygen. Okay, here one oxygen, here one oxygen. But there is a change in number of hydrogens. That's why, so nitrosobenzene, conversion of nitrosobenzene into phenyl hydroxylamine is also a reduction reaction. So this also unstable further reduces to aniline. So what is happening here in this step also? You see, phenyl hydroxylamine is converted into aniline. Aminobenzene is called aniline. aminobenzene. So in the benzene, one hydrogen is replaced by amino group. It is called aniline. It is a common name, aminobenzene. So when phenyl hydroxylamine reduces to undergo reaction with reducing agent, any reducing agent, it is giving corresponding aniline. So that means what is happening here? One loss of one oxygen. One oxygen is getting lost by this phenyl hydroxylamine. That's why loss of oxygen is also known as reduction. So all these are reducing reactions. That's why in aniline, when nitrobenzene, when undergo reduction reaction in presence of different reducing agents, it is giving this series of reactions. Finally, it is giving aminobenzene, which is stable. But in all reducing agents, doesn't give all these reactions, and depending upon the nature of reducing agent, it gives a different product. So we will learn this reaction, this reduction of nitrobenzene in acidic media and catalytic hydrogenation and basic media and in neutral media. So nitrobenzene undergo reduction reaction. We will study this reaction in detail. Okay, so first nitrobenzene. Nitrobenzene in presence of tin HCl. Tin HCl is a reducing agent which provides required number of hydrogens. So whenever nitrobenzene is reacted with the tin mixture of tin and HCl, it is giving aniline. So what is happening here? You see, tin and HCl. Tin and HCl is providing 6 atoms of hydrogen. So actually, when nitrobenzene is reacted with this reagent, it gives aniline plus water. So what if you combine this reaction? 3 moles of water. So what is happening here? Nitro group is converting into amino group. You see, once again, nitro group is converting into amino group. You can say this is a reduction reaction. In this reaction, oxygens losing, nitrobenzene losing oxygens, at the same time gaining hydrogens. In both ways, we can define this reaction as a reducing agent, reduction reaction. That's why this agent is called reducing agent. So once again, nitrobenzene, when it reacts with tin HCl, it gives aminobenzene. So since it is a reduction reaction. So anyhow, in acidic medium, nitrobenzene in acidic medium, when they react with any reducing agent, it gives aniline. This is a one type of reduction reaction. Okay. Then you see reduction reaction of nitrobenzene in neutral media. This is neutral media. We say in the previous slide, we studied acidic medium. It is neutral medium. So zinc dust and ammonium chloride provides neutral medium, not acidic or not basic. So whenever nitrobenzene reacts with this neutral medium, it is giving phenyl hydroxylamine. So NH2OH is hydroxylamine. This is hydroxylamine. So in place of one hydrogen, it is phenyl group is linked. That's why it is called phenyl hydroxylamine. So in the course of reaction, first nitrosobenzene takes place. Formation of nitrosobenzene taking place. So you see, this is nitrosobenzene. It is given in the square brackets. That's why it is unstable, intermediate compound. That means nitrobenzene is first converted into nitrosobenzene. So it means it lost one oxygen. What happened? This lost oxygen react with two hydrogens. It will be as a water molecule. That's why it is a reduction reaction. Then this nitrosobenzene is unstable. Further undergo reduction reaction with the same reagent. It is giving phenyl hydroxylamine. So anyhow, so nitrobenzene in neutral media. So zinc dust and ammonium chloride provides required number of hydrogens. At the same time, it acts as neutral medium, neither acidic nor basic. So that's why it is called neutral medium. So neutral medium, nitrobenzene in neutral medium, it reduces to give phenyl hydroxylamine. So in the acidic medium, we are getting aniline. In the neutral medium, we are getting phenyl hydroxylamine. Next, alkaline medium, that means basic medium. You see, nitrobenzene, when they react with any reducing agent, it gives first nitrobenzene. This nitrobenzene is unstable. Nitrobenzene in alkaline medium, it gives mixture of two compounds. One is nitrobenzene and one is phenyl hydroxylamine. These two phenyl and nitrobenzene and phenyl hydroxylamine combines in the other step. You see, this is 1 and 2. This is 1. This is 1. This is 2. So in alkaline medium, in basic medium, what is basic medium? Zinc and KOH. Or there are different alkaline mediums. You see, sodium arsenate NaOH, zinc dust and methanolic NaOH, zinc dust and aqueous NaOH. All these three acts as basic media. So different basic media will get different products. So what are the basic reducing agents of basic media? You see, okay, right. Okay, this one. So first nitrobenzene, in the first step it gives nitrobenzene and phenyl hydroxylamine 1 and 2. By combining this 1 and 2, by losing one water molecule, we are getting azoxybenzene. You see carefully, this is azoxy group, NNO. Azo, this is azo group, one oxygen there, azoxybenzene. This azoxybenzene undergo reduction reaction to further reduce by reducing azobenzene. Why we are calling reduction reaction? Losing of one oxygen atom. So in this reaction, this is also unstable. Finally, under reduction reaction, by adding two hydrogens to this azobenzene, we are getting hydrozobenzene. This is hydrozo group. NH2 is hydrazine. We know that. In place of one hydrogen, one phenyl group. In another hydrogen, one more phenyl group. That's why it is called hydrozobenzene. We know NH2 and NH2 is called hydrazine. So this hydrogen, in this hydrogen, two hydrogens are replaced by two phenyl groups. That's why we call as hydrozobenzene. So once again, I am telling what nitrobenzene in alkaline medium, it is giving with different compounds depending upon reducing agent. Sodium arsenate and you see in presence of sodium arsenate and NaOH, it is giving azoxybenzene. Whereas sodium zinc dust and methanol, it is giving azobenzene. You see, methanolic NaOH. In zinc dust and aqueous NaOH, it is giving hydrozobenzene. You see, we are getting three types of products. So different products. So one is azoxybenzene, azobenzene, hydrozobenzene. So these are the three reduced products. So these products, formation of these products depending upon nature of reducing agent. Sodium, or if you use sodium arsenate NaOH, you are getting this compound azoxybenzene. If you are using zinc dust and methanolic NaOH, you are getting azobenzene. If you are using zinc dust and aqueous NaOH, it is giving hydrozobenzene. So all these three reagents act as what? Basic media. So in general, nitrobenzene, when they react with the reducing agents like zinc dust and NaOH, that means alkaline medium, it is giving reduced products like azoxybenzene, azobenzene or hydrozobenzene. So this is about alkaline media. So acidic medium and lean. Neutral medium, hydroxylamine. In alkaline medium, depending upon the reducing agent, we get azoxybenzene or azobenzene or hydrozobenzene. Coming to the electrolytic reduction of nitrobenzene. You know what is electrolysis? So cathode, anode, electrolyte, reduction reaction, oxide reaction taking place in the electrolysis reaction. So when we electrolyze in electrolytic reaction, nitrobenzene gives different products depending upon nature of medium. Once again, so electrolytic reaction, nitrobenzene in weakly acidic reaction, weakly acidic medium, it is giving aniline. In weakly acidic medium, it is giving aniline. Whereas same reaction in strong acidic medium, it is giving hydroxylamine. This is hydroxylamine. You see, in strong acidic reaction condition, it is giving hydroxylamine. It is rearrangement given to para-aminophenol. Okay. Electrolytic reduction of nitrobenzene in alkaline medium forms all mono and dinuclear products of both mentioned. We just now discussed what is that azoxybenzene and azobenzene and hydrozobenzene. So we get a mixture of these compounds. Once again, electrolytic reduction of nitrobenzene in acidic medium, weakly acidic medium, will get aniline. Strongly acidic medium, first it is phenyl hydroxylamine, it rearranges to para-aminophenol. Whereas in alkaline conditions, we will get mixture of the compounds. What are those? Azoxybenzene, azobenzene and hydrozobenzene. This is electrolytic reduction of nitrobenzene. Once again, one more reduction reaction. This is a reduction with ammonium sulfide or ammonium hydrogen sulfide. You see, this is ammonium sulfide. This is ammonium sulfide, NH4,2S. This is ammonium hydrogen sulfide. Both are acting as reducing agents. When we use these reducing agents, whenever in benzene two nitro groups are there, one of the nitro group, only one nitro group is only converts into corresponding reduced product and amino group. So other nitro group intact, doesn't undergo reduction. So this is and that means ammonium sulfide or ammonium hydrogen sulfide selectively reduces only one nitro group whenever two or more nitro groups present in the reactant. For example, metadinitrobenzene, when it reacts with the ammonium sulfide or ammonium hydrogen sulfide, it is giving metanitroaniline. So I repeat, in the starting compound, we have two nitro groups. In the product, only one nitro group is reduced to amino group. Other nitro group is as such. That's why this reagent is used whenever there are more number of nitro groups. We require to convert only one group into corresponding reduced amino group. So in the other example, you see, this is para-nitro-dinitrobenzene. This is metadinitrobenzene. This is a para-dinitrobenzene. So para-dinitrobenzene, when it reacts with the ammonium sulfide or ammonium hydrogen sulfide, it is giving, you see, para-nitroaniline. So out of two, only one nitro group is reduced to amino group. So that's why in the selective reduction of nitro group, we use this specific reagent. Which one? Either ammonium sulfide or ammonium hydrogen sulfide. This group selectively reduces only one nitro group which is attached to the benzene ring. Okay, these are the different reduction reactions of nitrobenzene. Once again, nitrobenzene in acidic medium, it gives aniline. Nitrobenzene in neutral medium, it gives phenyl hydroxylamine. Nitrobenzene in alkaline medium, it gives a different mixture of compounds, azoxybenzene, azobenzene and hydroxybenzene depending upon nature of the reducing agent we used. In electrolysis also it gives various type of products. In weakly acidic medium it is giving aniline. In strongly acidic medium it is giving phenyl hydroxylamine, which is undergoing rearrangement by giving para-aminophenol. Whereas same nitrobenzene in electrolytic condition electrolysis it is giving mixture of products in alkaline medium. So this is and finally nitrobenzene, whenever in benzene more than 2 or more number of nitro groups, we will ammonium sulfide or ammonium hydrogen sulfide selectively reduces only one nitro group, remaining nitro groups are intact. So this is a selective reducing agent. So okay, this is a different reduction reactions of nitrobenzene. Finally, uses of nitrobenzene. Nitrobenzene is used in the manufacture of aniline and azo dye. You know what is dye? Dyes are used to color the especially cloths. Okay, textile industry. In the textile industry, we use dyes to color the different clothes. So in the preparation of dyes, aniline is used. So the preparation of aniline, we require nitrobenzene. So nitrobenzene is used in manufacture of aniline and also azo dyes. Nitrobenzene we use nitrobenzene in manufacture of floor polishes. Next, this is also used in scenting cheap soaps, low cost soaps. Especially this is a oxidizing. This is a very important one. Nitrobenzene used as oxidizing agent in organic synthesis. So in organic synthesis, we'll convert one compound into other compound, say where we require some oxidizing and reducing agents. So nitrobenzene acts as nitro oxidizing agent of different used in different reactions. Trinitrobenzene and picric acids are employed for the identification of aromatic polynuclear hydrocarbons as these form adducts with the latter products. So anyhow, trinitrobenzene and picric acids, in the preparation of these compounds also we use nitrobenzene, which are used to identify the aromatic polynuclear hydrocarbons. We'll do this practical in the PG. So 2,4,6-trinitrotoluene, which is called as TNT, it is an explosive. Generally, more number of nitro groups are present in an organic compound. It has some explosive nature. Trinitrotoluene also a explosive, and nitroglycerin. All generally nitro compounds, when we have more number of nitro groups in organic compound, we suspect that should be an explosive. So in this way, these are the different uses of nitrobenzene. So this is a chapter. So in this chapter, what we have learned? Aromatic nitrohydrocarbons. What are? I am giving one more recap of today's lesson. What are aromatic nitrohydrocarbons? Examples: nitrobenzene, nitroaniline, etc. Nomenclature. Then reactivity and orientation. So when coming to the reactivity, nitrobenzene is very less reactive when we compare to benzene or toluene regarding electrophilic substitution reactions. Why? Because of minus mesomeric effect, negative mesomeric effect of nitro group. It deactivates, it attracts electrons from benzene ring. That's why thereby it undergo deactivation. It is very less reactive towards electrophilic substitution reaction. In rigorous conditions, it takes place, very less product is formed, but this product is there's an incoming new electrophile occupies only meta positions to the nitro group. So that's why nitro group acts as meta director. Then coming to the reactions, we studied different reduction reactions in this chapter. What are those? Once again, in acidic condition, we are getting aniline. In neutral condition, we are getting phenyl hydroxylamine. In alkaline condition, we get a mixture of products depending upon the nature of reducing agent we used. Those are azoxybenzene or azobenzene or hydrazobenzene. And in electrolysis also, depending upon different media, we get various mixture of products. And ammonium hydrogen sulfide is used to selectively reduce only one nitro group whenever there are more number of nitro groups present in the aromatic hydrocarbon. Finally, we learned what are the uses of different use of nitrohydrocarbons. With this, we are concluding our chapter, nitrohydrocarbons. Thank you very much.